Hi, everybody. Thank you for joining us for the last session in the Chandra Frontiers in Time Domain Science. This is the closing session, which will feature a summary talk by Jon Miller. I want to thank everyone that's joined us over the entire month for the Chandra Frontiers in Time Domain Science. It's been a lot of fun seeing all of our speakers and a lot of fun bringing their science to you through the workshop format. I'd like to remind you all of the Scientific Organizing Committee who helped make this possible by selecting such a great group of invited speakers and contributed talks and lightning talks for all of the sessions that we heard. Their names are displayed here. And of course, I'd like to thank the organizing committee for making this possible as well and their help making this workshop a success. Without further ado, I'd like to introduce Pat Slane, the new director of the Chandra X-Ray Center, who's going to say a few words and introduce our speaker.
Okay, thanks, Rudy. I just want to first thank everybody who has contributed to this workshop. It's been an interesting organizational ordeal, I guess I could say, stretching out over a long time period, and there's been good participation all the way along. I think that's really been great, and I really want to give Rudy a big thanks for all of his organization, his great moderating of the sessions. It's really been a big task, and we all appreciate it. I want to say that I think everybody in our community would agree that a large number of Chandra's most exciting results have come from what could broadly be classified as time domain studies. I'm wearing my GW 150914 t-shirt in solidarity with the group here, even though I realize it doesn't have an electromagnetic counterpart. But we do all recognize the great importance and interest in the time domain areas of research. And I think we have a long history of helping to contribute to that. We work closely with many members of the community to help facilitate that, and we look forward to continuing to do that. What's been clear leading up to, and certainly within this workshop, is that new facilities like LIGO / Virgo, ZTF, VRO, these are all providing new opportunities, and they're going to lead to new discoveries and open new areas of investigation that are going to be of great interest and importance to all of us. And we recognize the role that Chandra can and must play in this area. So we're giving a lot of thought to how we can most effectively support this expanding field, and we're certainly taking a lot away from this workshop. I will say that this workshop should be thought of as really a first step or a single step in the process. We were already capturing ideas that had been put forth during the workshop. We're discussing them. We have plans to form a working group to discuss prospects for addressing these and other ideas that come up and moving forward on that in the upcoming year. Things to keep in mind for the people in this community. I think it's fair to point out that it's not a surprise to hear a topical area or a research area that feels like it really needs more Chandra time. We've heard this from many of our workshops. So for every more TOOs request that we get, geez, we'd like more time in the LMC, even though it's at a high ecliptic latitude. We'd love more time on solar system objects. We listen to all of them. We do as best as we can, and we're listening here as well. There was mention of automated TOOs. I will just say right now that that's just simply not in the cards. Chandra's not designed for that, but we have really done a lot to make it so that our system for responding to TOOs is as, quote, automated as can be, given the number of people who are involved. And I think Jon will say some words about that along the way. I would emphasize a few things to this community. When you do have TOOs and you send them to us, be very clear about, well, when you propose them, be very clear about your trigger criteria. When you submit them, make a simple checklist to tell us exactly how all those criteria have been met. It will really facilitate the process and make things go faster. Feel free to send me an email with a heads up or questions about the possibility for triggering one. That helps a lot and can get us going quickly. Why is it that you all wait until late Friday afternoons? That's the big question I have for you. One other thing, totally feel free to send me a one-slide summary of the cool results that you've gotten from your TOO. I will happily send them out to the team that has done all the work to plan them. They do enjoy seeing that sort of thing. So with no further ado, thanks again for doing this. It's been helpful. It's been interesting. And I'd like to now introduce Jon Miller, who is going to talk to us about a grand overview of this. Jon comes to us, as I think most of you know, from the University of Michigan, but he was an undergrad at Penn State, a grad student at MIT, and an NSF fellow at CFA. So he's been around Chandra folks forever. Not only that, he was the chair of the Chandra Users Committee in past times as well. So Jon brings a healthy bit of history with the mission and of course with doing time domain science with Chandra. So Jon's going to tell us about reflections on time domain science and Chandra.
Thank you, Pat. All right. I'm very excited to be able to talk to this conference today. I've really enjoyed listening to all of the talks 2 or 3 times a week. This was a really welcome scientific boost, and I'm so grateful for it. And it was so amazing to see the rich diversity of science that's still being done in time domain areas with Chandra. And the discovery space seems to be as rich as it ever was and potentially getting richer all of the time. So I think this has been a very, very positive experience. Partly owing to the fact that so much of the science spans different areas, and partly owing to the fact that the talks will be available later, I thought that just running through and trying to summarize all of them may not afford a lot of connectivity. So instead, I've constructed sort of a different summary talk where I think partly what I can do to some degree on behalf of our community perhaps is to try to acknowledge the tremendous effort that Chandra puts forward to make time domain science possible. And maybe I can give people who aren't quite fully aware of what it takes a little bit of an inside look at what's required to make time domain science possible with Chandra. Then I think I would like to try to highlight some of the current and I think enduring strengths of Chandra, things that will continue to set it apart. And many of these things are elements of time domain astronomy that were kind of implicit in a lot of the talks and sort of an undercurrent that threaded through many of them. And I would like to just bring them out a little bit. And then to wrap up, I have some questions and maybe a couple of ideas for the community to consider. If not in the discussion, then maybe just as you think about it in the back of your head when you walk around the block or have dinner. So first of all, let me say thank you to Rudy Montez. This was such a well-organized and smooth conference. To do this, I know, because he replied to emails from me at some points, that he was doing many things at once, but we never perceived that when we watched the talks. It was super organized. And I also found that Rudy was extremely supportive and patient. In no circumstance, when somebody was having trouble getting something to work, was he anything other than completely patient and helpful. And I think that created a welcoming atmosphere and helped everything to go extremely well. I hope that, by this time next year, we could all meet in person, but it's possible that that will not be the case. Zoom meetings may be with us for a little while longer, and I think certainly Rudy has set a standard, but I sort of suspect that this kind of meeting will be with us even when we can get together, because it affords people who can't travel the opportunity to participate. And I think a lot of the things that we've seen here and the way the conference has been constructed can really make those experiences better in the future. And so let me also just add to Rudy's voice in thanking the local organizing community and the scientific organizing committee. I think, again, it was great. And despite the fact that it's a Zoom conference, between the diversity of the science that's represented, the diversity of the people attending and giving talks, the nature of the in-depth talks, the rapid-fire talks, and then the panels, to me, it still had every bit the feel of and quality of a typical Chandra workshop and conference. So I think that that was a particularly difficult thing to pull off in this circumstance, and this team did it, so thank you. And now I'd like to spend a few minutes thanking Belinda Wilkes. As you know, she's stepped down as the director of Chandra this year, but I think our community owes her a great deal. The phrase that came to mind when I thought about how to start thanking her was that she took a great observatory and made it even better. And I think it's fair to say that, as telescopes age, some difficulties arise. And whether it's issues with gyroscopes or pointing or power or contamination or what have you, it's natural, and Chandra has had its share. But I think the community has felt especially little impact from that. And I think that that's really down to Belinda meeting these challenges and getting the team through it and maintaining an air of high morale and positivity throughout. And I'm sure that it wasn't in any way easy at any point, but she's managed it. It's the case that without a director that is actively in support of time domain astronomy, it just wouldn't happen. And especially in the face of these challenges and other difficulties with pointing flexibility, it would have been easy to, I think, scale back the TOO program or the DDT program. But instead, Belinda was always on the side of that kind of science. And I think it's made a big difference to the community, to me personally as well. Some of you may know that Belinda led the peer review for many years. And I know that in that context, she was a very strong advocate for better transparency, always in the corner of fairness, and always an advocate for proposers. So thanks is due to that effort as well. And although it's a little bit unfair, I think when you're the director of the Chandra Observatory, you are kind of the unofficial leader of the Xray community. And whenever I saw Belinda give a talk in that capacity, there was always tremendous positivity and an optimistic vision for the future, especially when we think about things like links. And that was so valuable and important. Now, the committees did a really good job of bringing a number of young people to speak at the conference. And I think a lot of the attendees were also young people. So I'll just mention for those people that Belinda did pioneering work in multi-wavelength studies of quasars going back to Einstein. This is one of her most important papers. This is an early look at quasars with Einstein, and it's just 24 quasars, but that's where you start. And the idea here was to look at whether or not there are differences in the spectra of radio loud and radio faint quasars. And it turns out that there are. Now, many people might look at the x-axis here and scratch their head about the energy index, just add 1, and it's the way you're used to thinking about it, I think. And you can see that there is, and the radio loud sources are harder than the radio quiet sources. And I think now, you are tempted to understand this in terms of relativistic beaming, flattening spectra, and in terms of different spectral components contributing depending on your viewing angle to the object. But this wasn't clear, without work like this. So truly pioneering work. And of course, it didn't stop there. Here I'm showing you the front page from Belinda's 2009 paper on the Swire legacy survey. This had Spitzer imaging, VLA imaging, and Chandra tiled the region, collecting over 775 sources at a magnitude down to 4 × 10⁻16 ergs per centimeter squared per second. I will say the true image that she made is a lot better than the one that I'm showing you. I blew up the contrast a little bit to make sure that it would pop on different kinds of screens. So Belinda has continued this work, and not only can we thank her for being an excellent director and being a tremendous help for our community, but we can thank her for her excellent science. And now we can look forward to even more of it. So as someone who's done a lot of TO observing, I thought it was time to try to pay homage really to the people who make this possible. And I put some slides together here with the help of Pat Slane. Let me say that immediately. So here we are. This is a fairly complicated plot that Pat helped to construct. So let me help you wade into it a little bit. The sort of pink boxes show you the teams involved in the process that transpires between the PI notifying the telescope and an observation being made. The blue boxes show you events in the process, and the green boxes try to map out the response team. Sorry, the response time. But notice what's being shown are sort of optimal response times. As we know, there are not many very fast triggers for Chandra. When a fast response is required, the end-to-end is something like 2 to 5 days, but there are many categories where this can proceed more slowly. As you look at this for a moment, I would like to try to sketch out the human side of this. So when a DDT or a TOO comes in, the director's office is involved, and so that means the director, maybe 2 other people from the director's office and the project scientist, and they evaluate the science justification for the DDT. If it's TOO, they look at whether or not the trigger criteria have really been met. Then they have to look to make sure that there's no competing proposals approved, either for targets of opportunity or through the regular GEO program. And they check their peer review to see whether or not the regular proposal review had in fact ruled against what's being proposed. Then the flight operations team mission planning group is involved, maybe 3 people from a 7-member team, and they begin to assess what opportunities exist in the schedule and to assess the impacts of trying to insert a TOO. This typically then means that the schedule has to be replanned, and potentially many schedules have to be replanned. And that team also begins to build command loads. The spacecraft engineering and ops team, maybe 5 of 11 people would be involved in this. They then have to look at the thermal considerations. As we know, that's a growing matter of concern for Chandra, but also things like the momentum and whether or not that's suitable for the observations that are being proposed or scheduled, and other aspects of point and control and aspect. The operations and science support team, maybe 5 of the 21 people involved there, then look at the instrument configuration and make sure that it's right, and thinks hard about the science modes and thinks about the instrument commands that will be necessary to execute the observations, and looks at aspect star catalogs. Then the science operation team mission planning crew, maybe 3 to 4 of 7 people, are involved with another look at schedule opportunities and impacts, this time with not just how the flight proceeds, but in terms of what it does with the science. And they generate observation requests, they review the schedule, and they start to look at load products. You may know that there are 3 Chandra flight directors, and typically one of them will then be responsible for reviewing the load that's being proposed and approving the flight products. The archive operations team, maybe 2 of 6 people, will then look to upload the coordinates into the database, look at offsets, all of the modes, and so on. And finally, as many as 3 of 6 people in the data processing team are going to be in charge of looking to support rapid processing requests. So it's an awful lot of people that have to get it right and do it quickly and balance, issues of the science and the spacecraft operations and the spacecraft safety. What I outlined here are the 26 or so CXC scientists and engineers are impacted by a TOO or a DDT request. And if not immediately, then certainly planning a new schedule, maybe several schedules, is very difficult, and they are going to be involved with that later. Of course, as we acknowledged at the end of the last session, there are always consequences for observations and observers who are getting bumped from the schedule. So there are impacts beyond just the Chandra team. The most important thing, and again, this came up at the end of the last couple of sessions, are the thermal constraints, which reduce the flexibility. Yet Chandra really retains, and I think, an astounding commitment to time domain astronomy and the TOO program. Maybe I can just remind you for a moment how some of this comes about. Well, Chandra's orbit, it proceeds about 1/3 of the way out to the lunar orbit. And when it's close to the Earth, it's passing in and out of the radiation belts. Many of you know that typically a successful mission lifetime is 2 years, and one hopes for something like 3 to 5. So now that we're at 21 or 22, we're into the uncharted territory, but the observatory still functions very well. However, everything ages, and nothing is improved with use, let's say. And this 2+ day orbit means that over its lifetime, Chandra has passed in and out of the radiation belts and dealt with particle radiation and other problems thousands of times. Eventually, the thermal blanketing starts to be less effective. There are impacts for acquisition cameras and other parts of the spacecraft. And so this is kind of natural. It's in some sense, what happens when you're fortunate enough to have an observatory that works so well for so long. The major impact is in pitch angle for pointing constraints. So Pat helped me put this together. This is what's known as the protractor plot, and it's showing you the different parts of the spacecraft systems that are impacted as a function of pitch angle. For those of you who would like a reminder, you can think about pitch angle. If you were flying in an airplane, it's are you climbing or are you descending? Roll is the axis about which the plane would roll if you were going to do a barrel roll. And yaw is the axis about which the plane would turn if you were only using the rudder. So this is a depiction of the pitch. Another way of understanding the impacts is this. And again, this is a slide put together with help from Pat. Here you can see the impacts and trade-offs, I think, especially clearly. At low pitch angles, you can, over here on the left, you can keep the aspect camera and ACES cold, which is good, but the thrusters get warm. So then you have to switch, and you can cool, say, the thrusters, but ACES is going to get hot. And there are other trade-offs at sort of moderate pitch angles. The bottom line is that, at this point in the mission, I don't think that there's any easy choices, and one has to constantly balance these different temperature sensitive aspects of the mission. So there's a real need to switch back and forth at a fairly high cadence. And this is, one of the things that impacts the ability of Chandra to do more fast TOOs and to coordinate and other things that are of concern to us. So Pat's taking over as director, and I think it must be acknowledged in this conference that probably nobody has had their pager go off at 3 a.m. more than Pat has as the former head of mission planning. I know that because I've worked with him to optimize some observations that he's put huge efforts into making TOOs work. And despite all of the burdens this has posed for him and for the team, he's still very amenable to time domain astronomy. So I think we're fortunate to have yet another advocate as director in the years ahead. So now I'd like to transition a little bit and try to bring to light a few of the things that came out during the conference that I think make Chandra special and make it a very important observatory for future time domain observations. The first of these is maybe less appreciated, though I think many of us kind of implicitly realize it, and that's the dynamic range of Chandra. So the limiting sensitivity that Belinda achieved in her observations, remember, is a few times 10 to the minus 16. That's fairly amazing on its own. It might be hard to do work on variability at the detection limit, since true variability can be difficult to distinguish from just counting variations. But the fact that you can detect things with the same observatory that you do time domain science at many higher decades is itself kind of amazing. Maybe one of the most important time domain observations that Chandra will make, of course, was the counterpart to 170817. And that flux was a couple of orders of magnitude higher than the limiting flux in Belinda's fields and in similar fields. This is 2 or 3 orders of magnitude below what's typical for an AGN, so it's especially faint. And I think one of the things that needs to be appreciated here is that not only did Chandra eventually make the detection, but it had the sensitivity to know that the mission in X-rays was really absent at earlier times. And so not just because you make the detection, but also because you start without a detection, you learn something about how the event unfolded. So it's really fortunate that early in gravitational wave astronomy, we had a mission that was able to achieve this kind of sensitivity and provide this important piece of information about how neutron star mergers occur. Sometimes it's possible to do time domain astronomy not just by TOOs, but when you accumulate enough exposure, as has been done with the Chandra Deep Field South and among other fields, you can begin to examine those deep exposures for variability in particular sources. And I believe we heard about this earlier. So This particular small source here, there's a zoom in of its relative intensity along the bottom here. This is Chandra Deep Field South X-ray Transient 1. I think most likely a tidal disruption event that was captured. This is getting up into the regime of some fainter Seyferts, but 2 orders of magnitude higher than the gravitational wave event. And then let me skip ahead to an observation that I think was particularly incredible, not necessarily scientifically, though I'm biased and thought that it was pretty great in that regard as well, but remarkable for what Chandra was willing to try. So V404 Sig is a stellar mass black hole and a recurrent transient. Chandra was willing to make 2 25 kilosecond observations when my then graduate student, Ashley King, proposed when the source went out into outburst in 2015. And what you can see is that it was so bright that even in just those 20 kiloseconds, we were able to take a number of flux selected spectra and examine the evolution of silicon and sulfur lines and iron lines as a function of flux. And in the lowest flux cases, which might not be the lowest mass accretion rate cases, the spectrum is strongly dominated by emission lines. In fact, they're so strong they can't be produced by the local continuum, which strongly suggests that the source was Compton thick at that time. And at the highest observed fluxes, which aren't necessarily the highest mass accretion rates, you can see evidence of P Cygni profiles. So a lot of science came out of some short observations. What's incredible to me is the guts it took to do this observation, and it really demonstrates, I think, how committed Chandra is to time domain astronomy. What I'm showing you now are a series of light curves from this 2015 outburst from Integral. So there's an optical monitor, the GEM-X cameras, which are soft X-rays 3 to 13, and then some harder X-ray cameras. In this panel, second from the top, the GEM-X light curve, I've added a red line to show you 1 crab, which is 2 times 10 to the minus 8 ergs per centimeter squared per second. The source was flaring to values very much higher than that. This is an incredibly bright transient when it flares. If you do the wrong thing, if there's an accident, it's possible that you could end up giving ASUS S3, everybody's favorite chip, a measurable fraction of its lifetime radiation dose. I think the easiest thing would have been for Chandra to say, absolutely not, we're not looking at this thing. Instead, Chandra decided to give it a shot. And the way this was achieved was not to place the aim point, not to place the source at the traditional source aim point on S3, because if it flared, even with the gratings in the way, there was still a risk. Rather, I think this is awfully inventive. The team decided that what could be done was to place the source just off of the chip and to work really hard at reconstructing the wavelength grid, though the 0th order wasn't visible. In this way, the strong source flux that's concentrated into something about the size of the PSF wasn't landing on the chip. The dispersed spectra could be captured, and the observation could proceed. And I think that's just amazing. So overall, what this means is that Chandra can do science over something like 8 or 9 decades of flux, and it can do time domain science over 6 or 7 decades in flux. I don't think that that's a capability that's reproduced by any other X-ray mission, and I think it will always mean that Chandra has an important role to play in time domain studies in the future. And on that note, maybe I can relate that to something that matters to me. So primarily, I'm interested in spectroscopy. And so I'm eagerly looking forward to the launch of Chrism in 2023, we think. It will fly an X-ray calorimeter If it follows the Hitomi path, then it will have a resolution of something like 5 EV in the iron K range. The resolution of the Chandra gratings in that range is about 45 EV. So it's roughly an order of magnitude improvement in resolution. And it's also roughly an order of magnitude improvement in collecting area. So on paper, it's going to be a big improvement, and it really, really will for things like AGN. For other sources, it's important to think about throughput, which is the product of the collecting area and the efficiency. And here I mean an overall efficiency, lots of individual things multiplied together. The calorimeter will have reduced efficiencies for brighter sources. So things like Xray binaries, maybe the brightest CVs, maybe the brightest flares from things like Markarian 421 and other blazars. So while Chandra has a small effective area, it has a high efficiency, so its throughput remains pretty high. For Chrism, the calorimeter, which is called Resolve, has a much higher effective area, but the efficiency for very bright sources, owing to the way the onboard electronics work, might be something like 5%. That means the product is low. So for science that depends on getting the maximum number of photons, it is still the case that Chandra will be preferable in some ways. Now, the sensitivity that's achieved in a line has something to do with the resolution of the spectrometer, not just with the number of photons, but regardless, what it illustrates is that Chandra is going to continue to be competitive even in the iron K band for bright sources. And I'll just end by saying that this number might be higher by the time of launch. The team is continuing to work on it, but whatever the case is, this is actually a function, and the efficiency will go down with increasing source brightness. I think another aspect of Chandra that will endure and continue to be important is its ability to do spectroscopy at low energies. So for this talk, I grabbed the Chandra spectrum of NGC 3783. It's a 900 kilosecond exposure. Chrism will have better resolution in the iron K band, but Chandra will continue to have better resolution below, say, 3 or 4 keV, depending on exactly what the final resolution of the calorimeter is on orbit. And there are obviously tons of lines that tell you a lot about the absorption and the winds and connections to the disk in this AGN and others. This is an important part of the band pass that is going to play a key role as we get a better look at the iron K band. And I think optimally, a future where one can study AGN and tidal disruption events and other things using at least quasi-simultaneous or contemporaneous Chandra and Chrism observations is going to be a good future. Thinking less about Chrism, it's important to remember as well that Chandra covers a bandpass that other missions, even XMM, doesn't. The combination of the low energy gratings and the HRC reaches down to 175 angstroms or 0.07 keV. And this band is one that can be important for studies of things like white dwarfs, TDEs, AGN stars, anything that's cool and has a strong emission line spectrum. What I'm showing you here is perhaps the best example of a spectrum taken with this particular configuration. This is a dwarf nova in super outburst WZ Sagittarius, often called WZ Sagetti. So there's an amazing signal to noise down here. And this capability, again, it's not reproduced by any other telescope. So going forward, it will really provide a unique window on a number of sources and a number of transient sources. And it's something that only Chandra will really be able to help us do. Now, I think the easy one is spatial resolution. Chandra will always be special in this regard. And I already gave you an example of why this is important. In 170817, the optical and infrared counterpart was known, At lower resolution, it may not have been as easy to pinpoint that the X-ray source is indeed coincident with the optical and infrared counterpart, but thanks to the unrivaled spatial resolution of Chandra, this was done concretely, and we know that it's the same source at the same time. So fantastic. Another example, and I chose one just sort of from the literature. There are many other examples. This is a Chandra image of a nearby galaxy, NGC 4636, and a lot of the sources surrounding here are globular clusters. And in looking at this observation, Jimmy Irwin found that in this globular cluster, there is this very interesting flare event where a source is observed to go from 10 to the 39 ergs per second up to 10 to the 41 ergs per second. And it does so in a very short time. This was a Nature paper because this kind of event doesn't have a precedent. It's not easy to associate it with known things. What makes it interesting, of course, is that it's in the globular cluster. This, at a lower spatial resolution, if you see an event like this, you might be tempted to say, well, it's a background AGN do funny things. But because of Chandra's exquisite spatial resolution, we know that it came from the globular cluster and that there's a very, very low chance that it came from some kind of background event. For me, I would still like to think that there are things like merging black holes or maybe intermediate mass black holes in at least some globular clusters. Perhaps it's possible to confuse a globular cluster and a stripped former dwarf galaxy that might have a black hole at its center. And maybe this somehow was involved in creating this flare. But it really is that spatial resolution that makes it interesting and important. And in this context and in many others, the spatial resolution of Chandra enables unique time domain science. So I have a few questions that I thought would be interesting to put to the people who have attended this conference. There's been so much interesting discussion and so many smart questions. I thought this would be an interesting exercise. So when we think about the wealth of science that's come out of, say, the deep field south, it's really remarkable. I mean, we learned about the demographics of AGN, black hole masses, the demographics of AGN relative to star-forming galaxies and normal galaxies. Those things all got separated out. The contributions to the X-ray background were made very clear. You learn about the history of ionizing radiation in the universe, which might have as much to do with accretion onto black holes as it does with stars. It's potentially one of Chandra's most important legacies. And to remind you, of something I showed you a few minutes ago, even in this field, it's possible to do some time domain science. So given that Chandra, it seems to me, always taps a discovery space when you put megaseconds into a problem, why not try to do that for time domain science? And so you could ask the question, what if Chandra put 4 to 8 megaseconds, similar to the investment in the deep fields, into TOOs in cycle 24? We can't do this. It's fun to think about, but even without the pointing constraints that currently exist, it would be difficult or impossible to do it. With the many pointing constraints that exist, I think that it's now completely infeasible. But maybe there are other things that could be considered. Maybe a cycle with an emphasis on time domain science rather than that huge overwhelming commitment could be considered. So one reason, in my view, why you might want to try this is Chandra does have this remarkable combination of unique abilities. Maybe you would like an early look at what links would be able to do in a future where X-ray triggering is just a small part of time domain astronomy, and where ground-based optical transient surveys, neutrino triggers, gravitational wave triggers, things from SKA, when those really dominate time domain astronomy. Maybe it would be interesting to see how much you can discover with a telescope that has very fine resolution, and to do so ahead of time so that you can be prepared when you do have a facility like LINX. If that were interesting, it would take not just a very strong scientific justification. Absolutely, that would be required. But I think it would take a great deal of unity in communication among the time domain community. And I'm not sure that's entirely natural. I mean, one of the brilliant things about this conference was the rich diversity of science that's being undertaken in the time domain with Chandra. But the community would have to come together and sort of unite behind such an effort. This would require joint white papers, communication through the community, communication to the telescope through the users committee, and so on. And so there are difficulties. And, the comments that came at the end of the last couple of sessions today about, we really would like more fast TOOs. We really would like more coordinated observations. I've always felt that way. It may be hard to achieve, but I thought of maybe one thing that is harder to reject quite as quickly. So this is one way of looking at the sky. If you're a Chandra mission planner, it might be a very familiar way of looking at the sky. So it outlines regions where, for instance, the guide star camera can cool, and regions where it's hot. So if you think about where you point when and how you have to flip between to keep different components happy, this is an important way to look at the sky. Maybe this is an opportunity, not just a difficulty or a matter of procedure. Maybe it's possible to make cool attitude zones and time domain astronomy work together. We know where the zones that work for Chandra are. You can know in advance when, say, E Rosita might be tiling that region. You can look at times when a host of ground-based observatories might also be able to tile that region, or when Swift might also be able to tile that region. And so you could perhaps set up an effort that would do so for part of a cycle. And what you might imagine here is that these partner telescopes, in the case of E Rosita, would be looking at this region naturally. In other cases, they might be making a special effort, but they might be willing to undertake some monitoring that's unusually intense for a short period at least. And when transient events are identified, maybe Chandra could try to devote more TOOs than normal since it's in a cool attitude zone. So a normal TOO that occurs in a random part of the sky, now it might be necessary to pre-cool the telescope before making that observation. So there's kind of a overhead of needing to do an observation to make the TOO observation. But if the cooling observation and the TOO observation are the same ones, maybe it would ease the scheduling, improve flexibility, and make everything work. And I'm just suggesting that this is potentially a possibility. It's something that, Pat would have to weigh in on, and many others, but something to think about perhaps. I think it might also be interesting to address with this crowd the future of Xray monitoring. Clearly, there is a growing and important component to time domain astronomy having to do with neutrino triggers and gravitational wave triggers. But a lot of the sources that were discussed in this conference still depend on having advanced knowledge of the Xray flux before you observe with Chandra. So it's worth taking a look at this. In some sense, I think we've had an embarrassment of riches. Swift is really terrific in this regard. And a lot of sources can be observed with Swift. In my own department, people use it for X-ray binaries, for AGN, for white dwarfs, for T Tauri stars, which you probably know are 1,000 times more X-ray active than main sequence stars. And they even use it for UV eclipses of stars by transiting planets. MAXI is better suited to bright sources. Its sensitivity is somewhat different owing to its design and its location on the ISS. Both of these are no longer young observatories. Swift is 16, MAXI is 11. It's possible, I think, based on things I've read recently in terms of overall health and consumables, that Chandra could have another 10 years. There's no reason to expect that things like Swift and MAXI might not be along for all of that journey. But instead of planning for the best, it's good to hope for the best and plan for other eventualities, let's say. What might that look like? One is ZVOM, I think is maybe a fair way to say it. This is a collaboration mainly between France and China. At least prior to COVID, it was scheduled to launch at the end of 2021, and it carries 4 instruments. And in many respects, it's kind of like a Swift, and in other respects, it's kind of like a small Swift. The Eclairs instrument extends down to a lower energy than does the BAT, but it's a coated mask camera that also has a 2-steradian field of view. The MXT, the micro-channel Xray telescope, is sensitive in about the same range as the Swift XRT. It also has a small field of view. And again, the idea is that when something is detected, the mission can swivel over quickly. The energy resolution of the MXT is sort of like a CCD. So that's very similar to Swift. It's just a bit smaller than Swift in terms of its collecting area. So whereas a half a kilosecond or a kilosecond with Swift will get down to a level of a few times 10 to the minus 13 ergs per centimeter squared per second, it takes 10 kiloseconds to get down to 10 to the minus 10, 1 times 10 to the minus 12, sorry, ergs per centimeter squared per second with the MXT, if all goes according to plan. So you're not quite as sensitive to things like AGN flares, TDEs, and so on. Of interest, I think, to many observers is how the data will be distributed and shared within the time domain community and broadly. So the core program on gamma ray bursts, ZVOM has a goal of sharing triggers within 30 seconds to the broader community and making the products public. So that's tremendously positive. There's a general observing program that includes things like Xray binaries and AGNs and ULXs, the usual suspects. And those will have a proprietary period of a year. TOOs are going to become public immediately, according to what I've read, with the exception of TOOs that are the product of missions that have a memorandum of understanding with ZVOM. Another bright sign for the future is the Einstein Probe. This is being led by the Chinese Academy of Sciences. Again, at least prior to COVID, it was going to launch at the end of 2022. So it's again something that could help to supply triggers for a host of sources for Chandra for the decade ahead. It operates in a survey mode so that it would try to get half of the sky every 3 orbits, and it's planned for low Earth orbit. And then as the year changes, it would get to the full sky maybe 3 times per year. The graphic that I could grab wasn't very good, so I managed to find a good picture of the WXT, this wide field X-ray telescope, on an optical bench. So I'm instead showing you this. And you can see already that what this really is a lobster eye camera that's going to have a 3,600 square degree field of view. So just larger than a stare radian. The Einstein Probe is really about grasp. And when we say grasp, we mean the effective area multiplied by the field of view. So the area of the wide field X-ray telescope, it's small. It's only 3 centimeters squared. That's orders of magnitude less than the telescopes you might be most familiar with. But the field of view is large, so the product ends up being large. And for instance, the grasp of the Einstein Probe will be an order of magnitude higher than even what's achieved with E Rosita. So it will not be optimized for very faint events, But for things like AGN flares, TDEs, and things at a similar flux, it will be able to detect these things readily, and there will be a bright future for following them up with Chandra. Just to kind of illustrate this point, though, so this plot shows you the limiting flux that can be achieved in normal units and in Crab units as a function of accumulated exposure time, assuming two different power law spectral indices and a very modest absorption for things out of the plane. A typical observation, I've added the green cross, by the way. A typical observation, if I read correctly, is going to be something like 20 minutes. So just over 1,000 seconds. And so typically that's going to reach down to many times 10 to the 12 as the limiting flux in a given pointing. So that sort of sets the scale for the sort of sources that you'll be sensitive to with the Einstein probe. So you could perhaps just detect the transient that Franz Bauer and colleagues reported from the Chandra Deep Field South, but you couldn't necessarily find the neutron star merger that has garnered so much attention by Troya and others. Maybe you really still will need Chandra for that for the decade ahead. So I think that, if everything goes to plan, even in the worst case scenario, there's still a bright future for X-ray monitoring, and that's very positive. I think that we won't have quite the sensitivity that we have now if we were to lose SWIFT, but I think that's just, sort of a testament to what an amazing facility SWIFT really is. And again, there's no reason to expect that we won't have it, but it's worth thinking about these sorts of things. And the last thing that I wanted to sort of point out for the people who have been listening, because I think it's important for our community. I've taken a picture off the web here. This is the ESO Extragalactic Explosive Universe Conference that was held over a year ago in Garching. One of the remarkable things about this photograph is how many young people are in the picture. That's different than the average astronomy conference, I would say. And when we look at the people giving talks and attending this conference, I think that there's more evidence that this is a field with a lot of young people within it. And that's tremendously positive. And I think the question is, how do we keep them in it? And I think that's part of our job as a community to think about those things and make sure we're making good choices. In this regard, I think one of the things that must be considered is the policy regarding how quickly it is possible to get hands-on data. So many time domain efforts have this policy of making data public immediately. And I think there's a very good argument to be made that speed and openness have benefits for the entire community. They lower barriers to entry. They allow results to be checked immediately. Things move forward in a very good way. Chandra has traditionally had at least the option of a proprietary period for observations. For TOOs, especially for DDTs, the director has the ability to either grant a proprietary period or not. In my view, I think this is a good thing. I think that it gives students a chance to lay claim to a result and to not be scooped by senior researchers that have more experience with the telescope or more experience in that area and can push out a result faster. Maybe not much faster, but sometimes in time domain astronomy, a little bit faster makes a lot of difference. In my view, protecting students that way and trying to thereby include more of them in the field and let them lay claim to important results is congruous with other efforts in the field. For instance, I think that it's similar in some regards to the ideas behind having anonymous proposals, where the goal is to improve inclusivity and to have more first-time proposers. So I think those things are aligned. That said, the era of time domain astronomy is different than the era astronomy was in 20 years ago. So I think it's possible that data policies, specifically with regard to transients, not for things like clusters or supernova remnants and so on, but policies for transients may need some sort of granularity in the future. It could be the case that one size simply won't fit all. My view remains that at least maintaining the possibility of having proprietary periods for students is important. And it's possible that the policy that Chandra has currently, where some of these decisions are down to the director's discretion, may be the degree of flexibility that enables the granularity that's needed and can best reflect the wishes of many different sub-communities within time domain astronomy. But I would say, perhaps as a final note, that, I think we have ample evidence that completely unregulated capitalism doesn't actually improve competition or innovation. We do better when we have things like patents and antitrust laws and so on. And it's meant to protect those who would innovate and need a little bit of time to sort of build that out. And I think that students are very much in that position. So to conclude, thank you very much for this opportunity to talk to you this afternoon. It's been a pleasure listening to this conference. Through a difficult month, it was really a boost to get to hear about so much exciting science. I know that for others, it is very difficult to find the time and the space and the mental clarity to be able to give a really good talk these days. And as far as I can tell, everybody did so. I think it was a really outstanding effort by all of the speakers, especially by the students and the young scientists that participated. I enjoyed listening to the question sessions and the panels as well. There were lots and lots of thoughtful and interesting questions. And I come away from this with tremendous optimism because the diversity of science that's being done 20 plus years into the mission is, I think, just completely staggering. And I'm sure that with new observatories coming online and new windows into the universe, things like neutrino triggers, that Chandra's unique capabilities will continue to make it the difference and open new discovery spaces. So thank you very much.
Thank you, Jon, for that excellent talk. I'd like to thank you again for speaking to everyone, and I think the questions that you posed provide a lot of food for thought for our community. I'm really grateful that you can do that, you could do that for us. I don't think we're going to take questions right now. So I'd like to thank everybody again, and I'd like to thank Jon again, and I'd like to thank Pat, and I'd like to thank all of the speakers, like you said, that were terrific. And I remind you all that you can find the videos online to view at your own time. Thanks again for joining us and making the Chandra Frontiers in Time Domain Science an excellent event. Bye, everybody.
Thanks, Rudy. Thanks, Jon.